This is a production of Cornell University.
So I'm going to be presenting today trying to understand the co-inheritance of two traits that are very important for our breeding program. We're using a method called regional co-heritability mapping. Now I'll go into that. So I have a picture about what conventional cassava looks like. It's mainly white to cream. And then this is what we call the yellow cassava, which is an effort by Harvest Plus to biofortify cassava with provitamin A. And so Harvest Plus, it's a program with the CG systems, and with cassava, the main target is provitamin A. And in fact, beta-carotene is the provitamin A that is targeted, but total carotenoids, which shows itself as yellow coloration of the flesh, it's a good proxy for measuring beta-carotene, because the process of measuring beta-carotene is HPLC, and it's kind of tedious. So we have a prevalent problem right now with the yellow cassava. The yellow cassava has drastically low dry matter content, and this is a problem because in fact the value of cassava is the dry matter content and the yield that we get per hectare. So there has been reports mainly in most African breeding programs of negative correlation between this dry matter and this yellow coloration of the tubers. And there have been counter reports in South America, like in SEAT or Colombia. They don't see this negative correlation. So we think it's majorly in the African germplasm. So the motivation is to understand the genetic basis of this negative correlation. And to do this, we employ a method. We term the regional co-heritability mapping, and I'll walk through the procedure. So the procedure starts by fitting a bivariate G-block model, and the traits are dry matter and B. B is a value from chromometer, I think that's what it's called, and it just measures the color. So we take the B and the dry matter trait. We fit a bivariate G-blob using this model, and in fact the way the model is fitted is that we have a stack of the two traits, and we fit the X matrix is in our model is just for the location effects, because the data was collected from multiple locations. And then we show the genomic effect in U, and here we show that this effect has covariance from two covariances, one from DK, which is a decomposition of the genomic relationship matrix that comes from markers, and VG, which is the trait by trait covariance matrix that we are estimating. And the same goes for error, and for error is simplified because we have an identity matrix showing no correlation between data points. And we fit this model, and then the next thing we back solve to get SNP effects from these values, from the genomic values. And SNP effects are estimated by multiplying the transpose of the marker matrix. This marker matrix is centered, multiplied by the inverse of the genomic relationship matrix, and the estimated genomic effect from each trait. So after you back solve, we try to standardize again using just like we make how we make a G matrix, using the denominator from Van Raden et al. 2008. And then the next thing is that we bin SNP effects. We bin chromosomes into segments, and these segments are unique 3,000 SNPs, and they are actually unique. There is no overlap, so we divide the chromosome into different segments. We term these genomic segments, and when we have bined them, of course, there are at the tail end of the chromosome, some of them are less than 3,000. So after binding them, we solve for clonal genomic segment values, and we estimate for this by multiplying the marker matrix again with the SNP effect that was calculated prior, and then we correlate this clonal genomic segment values with clonal for dry matter and clonal genomic segment values for the B trait. And this is how we get the correlation for each segment. So these were modeled using BLOP-F90 programs, and other matrix computations were done in R. So the data for the analysis was majorly genetic gain population. Genetic gain is a breeding population from the IITA, and it has been bred since the 70s. So we use only data collected in 2 years. So we use the dry matter and the B trait, as I said previously, but we have a second trait we call, a third trait we call pulp color, and this is a binary trait that actually measures the color of the root, which is 1 for white, and then 2 for deep cream to yellow. We use about this number of GBS SNPs, 451 clones for white, 262 clones for yellow. Data was from 3 locations, and we do this analysis in all the populations, white, yellow, and white plus yellow. Excuse me. So this is the result from white plus yellow. So each bar is 3,000 SNP segment. Each color, so as you go from black to red to black to red, so each color difference is a new chromosome. And what we see from this analysis is, if you look at the scales, this here in Y is the estimated genetic correlation, and in X, of course, is the chromosomes. We see an overwhelmingly negative correlation at chromosome 1, and then it seems that other chromosomes are a bit slight or neutral. This is for both white and yellow populations. And we move to the white, we see a different result. If you look at the scales of the genetic correlation, in white we observe like a strong correlation here, not strong in terms of the value, but this segment shows very strong correlation. And then we also see something here, that most of the segments in white are positive. We observe positive correlations. So if we move to yellow, we see something that we see something we saw in the previous one with white and yellow, but a different thing now occurs is that we see that almost, in fact, all, apart from the neutral ones, are overwhelmingly negatively correlated for the yellow. So what does this show? Before we go to discussion, I want to show this genetic correlation from the bivariate model itself, not the mapping. And in white, we observe a positive correlation. In yellow, we observe a strong negative correlation. And when you have both, we have a weak negative correlation. So the correlations tend to be consistent between these and the maps. And we observe a very strong negative correlation for the yellow. So what does this mean for the program? It means that this favors development of high dry matter white varieties, And in fact, this product is already in high demand in Africa, both for the food and starch industries. And we will recommend a separate breeding program for this. And then if you move to yellow, we observe overwhelmingly that it doesn't favor yellow variety development. And this is indeed discouraging because of the high hopes we have for Harvest Plus. But there has been a lot of effort already towards this, and in fact, a lot of clones are brought in from SEAT and used in the breeding program for this, and it's ongoing now. We'll see the result. And it's also a good target for CRISPR if we find what is going on completely. And in fact, there is also a chance that there can be a recombinant. Who knows when this happens. And in conclusion, I want to highlight what is going on in chromosome 1. Chromosome 1 is one that we know already that there is an introgression that happened in the 30s or after that as well in most cultivated cassava in Africa. And chromosome 1 seems to be the culprit in this case, but chromosome 1 is also good for dry matter, so it's a very difficult case. And we're actually showing the methodology because it shows very good way to see what is going on between these two traits. And in the end, we think there will be some progress from the results. Thank you very much.
This has been a production of Cornell University, on the web at cornell.edu.